Our next speaker is Dr. ZhongtaoFu, who is the Chief Architect of HYC technology. He leads the HYC semiconductor.
By the way, Ian, I don't see your screen or presentation.
Oh, you're not able to see my screen? Oh,
not yet.
Okay, let me share again. Let me share here. Are you able to see now?
Yeah.
Okay, cool. Yeah. So Dr. ZhongtaoFu is the chief architect of HYC technology. He leads the HYC semiconductor division on a path to provide solutions for global semiconductor industry of IC and system test. He also is responsible for identifying new technologies as well as developing the fundamental technology capability. He built the first ever automated test equipment for HYC semiconductor division and led the team and developed the most widely deployed tester in a quantity of thousands battery management system tester, which was acknowledged as the most critical to the success of HYC in 2019. Recently, he architected the RF tester, TS1800, deployed it in the 3 major RFIC manufacturing test floors at HYC. Before at HYC, he was senior staff engineer at Maxim Integrated. He led the audio amplifier testing as a senior staff engineer. And he was responsible for the e-test metrology development at Intel before that as a senior engineer. He has a publication of more than 20 papers in the field of mixed signal VLSI design. Dr. Fu got his PhD from Cornell University in New York and bachelor's in telecom engineering from Hefei University of Technology in China. So without further ado, let's welcome Dr. ZhongtaoFu, who will give his speech titled ATE Technology Must Keep Up with the Evolving IC Technology. Thank you.
Okay, let me share my screen. Let me know if you can see it.
Yes. Yeah.
All right, great. First of all, thanks for the opportunity to meet with Chinese American Semiconductor Professional Association. It's a pleasure to talk with you and get to know each other. I'm located in Vancouver, Washington. I see this as a great bridging with Silicon Valley and the rest of the world. So an overview of today's presentation. We're going to talk about the ATE market forecast and identified ATE industries, and also a little bit ATE introduction for those of you who are new to this area, and maybe just a review for you who are seasoned ATE veterans. Then a few product examples, and then we're going to talk about the system level test. Many years ago, I graduated with research thesis on PLL IC design. I took my first job at Intel in semiconductor test. Well, at that time, my advisor came to me and asked, "Hey, you work on circuit design for so many years and made great impact to this area. Why do you do test?" At that time, I was working on clock circuitry at the time, and my main focus is to reduce the phase noise of the clock circuitry. I was able to get the phase noise as low as the atomic clock and all kinds of modifications inside out of that circuit. I told her that I enjoyed circuit design, but only on few specific circuits. I look at test as a much broader area and decided that's the area I want to explore. Well, 12 years later now, I'm still in test, and test is ever evolving. Let me. Okay. Okay. Now I'm. Well. Okay. 12 years later, I'm still here. Test is evolving with the same speed as semiconductor industry, or together with the real world problems that we need to solve. It's getting more and more interesting. Okay. I did some research on multiple market outlook sources, and they all came back with one signal that the ATE market is growing and is growing fast. Based on the research in the market, the global ATE market was at close to 6 billion in 2020 and 7 billion in 2021, and expected to be reaching 9 billion in 2028. So the dollar amount is only one part of the market, but that is a clear indicator of where the industry is going. The global ATE market is driven by the rising demand for data collecting and testing various electronics in different industries. As you know, penetrating of the smartphones, consumer electronics, and the highly integrated SoC designs, and also the growing content in the automotive sector. As a result of growing tendency towards the low-cost consumer electronics, and that ATE is expect to drive the ATE market in the coming years. Well, I got to show you this, the emerging market in AI and virtual reality, and those glasses are fantastic. And also in the as the electrical vehicle are coming up strong, there are numerous electrical components in the cars, especially the self-driving segment. Well, I've opened up one of the Oculus glasses the other day. It's amazing how dense they pack this thing. It's got the optics, it's got the GPU, memory, RF transceiver, antenna, all in there. It's just like a smartphone. I'm amazed. So back to the ATE market drivers. I see the trend of going a consumer electronics for low-cost alternatives and large volume, and also little human interaction, meaning factory automation. I brought up a few charts. If you look at this one, ATE market can be segmented based on type of product, application, or geographical location. Especially this chart, you can see that geographically, the global ATE market is dominated by North America, whose market share is expected to grow further. The global market of Asia is what I want to point out. It's growing at the growth rate of 3 to 4%. In the same forecasted period, Asian market is expected to become the largest regional segment. Well, that's due to the growing number of smart electronic devices and the Internet of Things in your house, in your home, and the workplace. The chart on the right, and you can see Taiwan, South Korea, Japan and China, they are almost going to double by the year of 2027. Well, we just talk about the segment based on geographical locations. Well, based on application, the main ATE market includes consumer electronics. That's where the ATE is used to assess the functionality of your smartphones, tablets, radios, and so on. In semiconductor fabrication and assembly, ATE is used to measure the output signal of the semiconductor devices to validate their functionality. Automotive and transportation, ATE is also used to test the functionality of various IC, including those in the ADAS, the self-driving assistant, on information system, battery, a braking unit, and those. Telecommunication, that's where you see the your cable modem and the gateway is being tested. Last but not least, the medical. The ATE is used to test numerous temperature monitors, pacemakers, ventilators, and etc. This is a typical semiconductor production chain, going from the original IC design and the wafer fabrication, and then there's the chip probing. After that is the packaging, is the dicing, packaging, and so on. The new product introduction, you need that's a final test 1. Production test, that's your final test 2. Even after you ship, there's failure analysis that's also require a test. The highlighted are the ones that all the tests are required. This is a typical production chain. You can see that test is throughout the whole production chain. Production test need to meet the following functions. The first one is need to catch the production defects early on. It's important to aware that the durability of your product before it reaches the customer, to avoid any issues with the customer's dissatisfaction or complaint. So you need to test before send it to the market. Also, it's responsible to find out what your product can endure. Stress test should be the integrated part of the production test in order to figure out what type of stress your product can endure, whether it's temperature, pressure, and so on. So throughout through the stress test, manufacturers can introduce real situations that the product will face during their life cycle without actually waiting the whole life cycle of the product. Also, production tests need to give insight to your system level function. While testing the function of your own product is beneficial, it's also necessary to test your product in the whole system, because your products only perform as good as the sum of the parts altogether combined. So you need to make sure your part will work with the rest of the system in harmony. The last, quality assurance. You need to make sure your product meets specific standard. That's one of the crucial requirement, especially for medical industry and also for radio frequency test. Your either phone or Wi-Fi device are required to meet FCC standard to ensure that your spectrum doesn't leak to others and others doesn't interfere with yours as well. Well, now comes to the actual ATE instrument. ATE is useful data acquisition and the diag tool. It's important that we distinguish the purpose of the instrument. The ones on the left, I put there, those are the lab instruments that are fully capable of many tests, but they are costly. They are like tens of hundreds of $1,000 per each. On the right is the ATE tester. They must fit in the production environment. They need to be low cost, highly automated, and it's got large number of throughputs. ATE consists like many components from the actual instrument to the handler, a socket, and dot board, load board. The tester is the heart of the system that includes the control hardware, sensor, software, who is collecting and analyzing the test result. Tester is the instrument or multiple instrument together perform a functional test or performance test to your product. During the test, a preset of patterns is sent to your DOT, and then the output is analyzed against a set of limit. The result is then passed to the handler. The one on the left hand is the handler. Handler is responsible for inking the failure units and separate the units to its own bin. Handlers are typically divided into multiple types, gravity type, a turret, or a pick and place. The socket is the one that housing the DOT, circle through thousands of units and make electrical connections without failure. That board is designed for a particular product, and it varies from product to product. A load board is on top of the instrument that's redistributing the resources in your tester. Those testers can cover majority of the products. We put them into digital. Those are the MCU, ASIC, logic, embedded RAM and flash, as well as analog. We put power management, like battery management, digital power supply, those analog op-amps, LDOs, even audios. Mixed signal test, ADC and DACs are in this category. RF test, those are RF front-end units, switch, LNA, tuner, filter, and so on. Over here, I would like to introduce one of the RF tester that we developed. This RF tester is going from low frequency to 6 gigahertz with a maximum power up to 35 dBm, and supports SPI, MIPI, and all other custom digital communication. It's got the noise figure test capability, and also it's got 16 bidirectional IF port, and also one high power input output. This tester is a PIXI based tester. PIXI based tester is a PIXI chassis with many functional PIXI cars. In this, as an example, going from the top, there's the digital power supply. It's got 4 power supply channels. Each of them can go up like 1.5 amp. Gaining them together, you reach 4 or 5 amps. The next one on the right is the PMU, capable of 200 megabits per second of digital testing. There's the VNA and also the VST providing S parameter measurement and the signal generator and analyzer. Further clockwise, that's the GPIO providing general purpose connection to the DUT. Audio card is not part of the RF system, but this audio card I like to highlight is got the super THD performance all the way up to 120, 130. BMU card is specially designed for a battery management unit test. It's a variant of the DPS design and also the SMU card. Looking into the whole tester as a system, it's got the industrial PC, and there are 2 options for Pixie chassis inside the tester. One is the 12 slot, the other is 6 slot for less number of resources. Pixie card, as I mentioned, those are the variety of functional cards. Also, a load box in the tester that's providing a reconfiguration of the resources and also port switching as well. Calibration box, and that one is going with all the is pairing with all the testers. That's providing a calibration on both frequency and the power, and also the typical VNA calibration as well. If you look at the typical radio frequency front end, those are the components in the whole system. Signal going in and out of the RF transceiver. On the TX chain, it's the power amplifier, duplex, switch, combiner, and antenna, and so on. Coming to the signal coming from the antenna, going back to the RX chain, there's the filter, the LNA. So the RF tester we developed can test all these components in the RF front end circuitry. A typical RF test includes the simple open short test that's accomplished by the DPS or PMU, and so also DC test that's to verify the device DC current voltage parameters. Also, there's E-flash test, functional test, and AC test. Those are being tested by the PMU. On the RF test, they are noise figure test, gain test, attenuation, and harmonic test. Harmonic test is one of the hard to achieve ones. You got to feed 30 dBm of power. In the meantime, got as low as -70 dB down of second and third harmonic. Also with two-tone test, you measure the IP3. For switches, you need to test the switch on and off time. S parameter accomplished by the VNA. Okay. Now let's switch the gear a little bit and talk about the system level test, SLT. System level test test a whole unit as it were used in the end use condition. To push more complex integration in chips and with more complex design and advanced packaging and new applications, system test is making this harder and harder, especially in the market as automotive, where the chips are expected to last like 20 more years. And also the number of tests required is increasing as the designs becomes more complicated. Therefore, test it. Well, sorry. Well, when you test the system in the end use condition, you're also adding crosstalk, jitter, noise, and all those real world deals to the system. Therefore, test it as a system becomes like an option to many manufacturers. Actually, SLT has been in the process for a long time. When the IC is the whole system, by putting a test sensor node on a corner of the die, well, doesn't tell you the whole picture. You need to put a test into the middle of the heart. The heart, I mean like the hotspot you found during the traffic test. So the focus for SLT is more than just a basic functional test. It's more about the traffic test. You need to boot up the system for traffic test. That's why SLT test time is significantly longer than traditional ATEs. Traditional ATEs, you test the chip at like seconds, a few seconds. Typical system level test can last up to like a minute. ATE differs from ATE in ATE differs from SLT in many ways, even though they share a lot of common instrument. For example, SLT gives you the test result of a go, no go, without telling you the performance margin like the ATE will do. ATE covers structure test and the parametric test. A typical logic scan will do that. Built-in self-test, more of a DFT function when you have the pattern generator built inside of your IC, and you do a loop back and test it with a JTAG. System level test is testing at end use function, and you need to either boot up the system with a USB or Ethernet, and then you test how the components working together as a system. A typical system level test cycle will look like this. This is a picture I've showed before from IC design, fab, chip probing, and then packaging, final test, and then there's the system level test. Many other tests are required, while the system level tests had been optional for 4 years. Don't forget that the test is always adding a cost to your product. No one is willing to pay 100% test or test more than necessary. Right. So balance the test time and the high quality had made this system level test on and off. By on and off, I mean even though SLT has been there for years, it's not new. The actual application of this technology had been limited to only few large chip makers. There are many other chip makers have not used system level tests yet. It's not applicable to them due to limited funding or resources. One of the SLT handler we provide last year is the EP3000 series. It's capable of testing a variety of device types from QFP, BGA, and so on, minimal of 2 millimeter by 2 millimeter by size. For system level test, UPH is a critical parameter gauging how efficient the system is. Well, as you can see, the index time is 11-13 seconds. Also jam rate is 1 out of 5,000. As the system get very complicated, and there are 128 sites in the system, jam rate is important to maintain a high throughput. Challenges in SLT, as you know, long test time requires high parallelism to be efficient. 128 site is what we have for now, and I've seen other companies going even higher in multiple site testing, and also handling diversified IP for all products has been challenged because they use different communication standard. So standardized communication interface can be a challenge. And also SLT is lower in or later in the process cycle. So you're gonna have a long steps between your device design and when you SLT test result come back. Here's what I see as the SLT. Standardized communication interface is one of them. High parallelism is one of them, and it's good for longer test for the product with longer test time and lower defect rate, and also the capability of tested at tri-temperature, from cold to room temperature to as high as 85 degrees. So system level test has begun gain attention in the market again. Like I said, it's been on and off, but now I'm seeing it's coming back. In summary, the global AT market is growing at high rate, and AT market has spanned multiple industries. Various market segments calls for low cost, high volume production, and high throughput solutions. At advanced technology nodes, with the emerging of new market with advanced packaging, test is going to look very different than the past. Hello, any questions?
Thank you.